It's a secret pattern. 1311 is the code, the secret code. I'm sure you found the pattern. There's no pattern. That is not random too. Okay, so let's see. Oh, you will still have 1 minute. Oh, did I start recording? That works. Primary audio source. Okay.
I don't know. It's mainly the ESL stuff that are messy. Like I can deal with you like not even if you want to but the other is like it's like oh it's just keep the normal ports like the vanilla plus. Because they have more like yeah, they have like a scalar element or something.
Okay, don't forget to do attendance. And let's get it started. We are still in pipeline topic. We want to see how we can improve performance without, changing the technology. So with pipeline, we can do that. The idea is to actually make clock per instruction as small as possible. One is the best one. If you can make it one, it's great. So how we can do that? Pipeline can help us with breaking down a big task to small pieces and do multiple tasks, share these pieces. So that's called pipeline. Sometimes works great, sometimes not. When it's not working fine, we call it hazards. We have different type of hazards. We started last week with a structural hazard. When the resource is not enough, we can add more resources. Instead of having one memory, we can have two memories, one for data, one for instruction. That helps for some instructions. Or we can use some resources like register file, multi-port sources. When it's multi-port, it means you can do reading and writing at the same time. It was also a trick that we said sometimes we can use different clock phases. It means in falling and rising edge, we can do different tasks, kind of sharing in one clock, two things. That was a structural hazard, mostly using duplication or hardware, we can solve it. Well, anyway, if we cannot solve it, we need to go for putting actually a stall. A stall is like a worst case scenario. We don't want to make a stall because a stall is just wasting processor's time. And then we move to data hazard. However, before data hazard, we talked about different stage of implementing a 5-stage pipeline processor in Verilog. In your book, in your reference book, Computer Organization, David Patterson, we are in chapter 4 of that book right now. End of this chapter, you have one extra, like an appendix, that actually has the code for RISC-V pipeline CPU. You just can take it and use it. It also has some methods for forwarding or fixing control hazards in that. Just like 2-3 pages code. I might ask you to run that and understand what's going on. It's very simple. This is exactly similar to that, but this is a simpler way. As you can see, we have different stages: instruction, fetch, decode, execute, memory, and write back. We need to define different registers for each one, and those registers kind of saving information when it's overlap with the other instruction, not bother, and we transfer those information to down, and anytime we need them, we use them. So we are kind of simulating those big registers that we call them pipeline registers in Verilog. We implement that. Anyway, I wanted to give another project that was related to your design, but I think that should be like another project maybe for if anybody interested to have extra credit, we can work on that. But for this, we're just gonna implement something similar to this, and is also in your book. You just can copy paste from the book. I'm gonna share with you the chapter when I make that project. After finishing this assignment that you already have, I'm gonna post that. Anyway, that's your new job to do. It's just normal what you did for the previous one cycle processor. This time it's 5 cycle. It has 5 stages, a pipeline. It's not that complex. You just need to implement some of these hazards that we're going to talk today and make some registers to make this processor work in different states. Okay, so this is what we covered last time, but still we are in data hazard. Data hazard has more to say. We're gonna talk about that more and move to control hazard as much as we can. Data hazard is something that happen a lot in assembly codes, happen a lot, and it's the situation that one instruction need the result of another instruction that is in top of that. We want something that is not available yet, even though it's the first instruction and we are after that, but still that's not available because we are in pipeline. We are sharing these stages. So forwarding is just adding some hardware to make this as soon as possible. We make some extra feedbacks, we have some buses, some cables, some bypasses to use those information as soon as possible. So we have different type of forwarding, but it's a hardware method. Forwarding is a hardware. We are doing with hardware. Of course, with software, we just can solve it easy. How we can solve it with software? I mean, the compiler. Any idea? We talk about it a lot. Like imagine 2 registers are, depend on each other. If you are using one register that is a destination of the previous register. So how we can solve that using software, using compiler or assembler? Stalling. Stalling, but yes, but any other method? Yeah, you can find also some other instructions that are they are independent instructions. We can put it in a stall, or we can do a stall too. However, a stall, yes, the best way is to not make a stall. A stall is a worst case scenario. Always you can put a stall, But the best way that compiler can work, if he's a smart compiler, can find some instructions that are independent and just put them, fill those gaps. And that's great idea, and it's going to be great. So that's how we work. So send data directly between pipeline stages, called forwarding. So from one stage to another, you just can have some feedback. You just can use those information. It needs some extra hardware and some controls. Of course, we need some control as well. So fixing these hazards needs one small control part as well, because you have some multiplexer and you need to find the select for those multiplexers. That a structure is like that. So we have different type of forward. This forward is called execution to execution. So imagine you got from the output of ILU one feedback to input. But here you need to put one multiplexer to decide which one go inside. So this called execution, EX to EX. As you can see, we get from execution to execution. We are not going somewhere else. We are just still in execution. And execution is combinational logic. You just can get one easily. You can get feedback from that. You can get from output to input. However, you just, when you get that, you need to have one multiplexer to decide which one goes in. So this is forwarding. This kind of forwarding called ALU, ALU data hazard. Okay, what about load? If you have load instruction, because load instruction, we are reading memory and put it inside register, and maybe we use that later. So we're going to have another type of forwarding that we're going to see that next slide. And in that one, we need the result of memory to be executed. So this is called memory, or is, yeah, how we can solve it. We can connect memory to execute. That's called load use, or sometimes called load ILU, because you get from load the result of load that is coming from memory to execute to one of the input of ILU. But this is kind of backward. We can't go in time. We can back in time, because time is going this way. Look at that. And we are kind of going back in time. So this is not possible. So that's why load use actually forwarding need one stall anyway. You know, you can't solve load use data hazard. This is also data hazard. You need one stall between. Do we have more another type of hazard? Yes, we have also load store data hazard. In load store, you need to get result of, so you're going to put another color, maybe this. You need to get from here and give it to here. This is called memory. From memory out, the output of memory get to input. This is called memory. Load store is another one. We have many other type of hazards, that data hazard that can happen. Like, for example, you can have branch that using some registers, for example. So you have ILU branch or ILU store. And so some of them can be solved together with this type of feedbacks, or forwarding or these hardwares, extra hardwares, some of them not. If not, we can do software. I mean, the compiler can detect them and just to do a stall, no operation or nothing, or replace them with another instructions or fill those gaps with another instruction. But we have these three feedbacks. When I'm saying execution to execution, means we are still in execution part. So this is okay because we are in the same time. But from memory to execution, we can go back. So this is not possible. We always need to put one stall between. So this is always software can solve it. We can do hardware as well, but hardware need to make a stall. Without the stall cannot solve it. We're going to see how hardware can make a stall. And this one, this dark blue, is memory to memory. The output of memory to input of memory. When you have load and store at the same time, and they have dependency. But we're going to see that later. But this example, let I clean this up. Just this blue one is normal, actually, ILU to ILU. So we are in the same time. We are not going past. We are not going forward. We are in the same time. So normally, we need two stall if we don't have forwarding. So we are saving two stall using this hardware. Why we need two stall? Because this subtract need x4 in decode. Need that here in decode. And it's going to write back here. Oh, actually, no, one stall. Why? Because write back and decode, they are using the data, they are using instruction registers. No, not instruction registers. Register files. That is the type of, it has a hardware that can do two things at the same time. We can read and write. That's why we have it two part here. So just need one stall. We need one stall here. The reason that we need just one stall, because instruction write back and instruction decode can do at the same time. Because the memory, the actually register file is multi-port register. That's the reason. Multi-port register file. That's the reason. Okay, so that's forwarding. We already talked about that last class as well. Let's go more deeper. Another type of data hazard is load use hazard, when you have a load and then use that. But this use is like ILU. So sometimes we call that load ILU, data hazard. Why is data hazard? Because we are accessing a data that is not still ready. That's called data hazard. So in this case, let's see what's happening. So imagine we have a load here, load double word, for example, x1, and x2 is the address. And here we have subtract. We have subtract x4, x1, x5. Okay, first of all, do we have dependency? Yes, because this is using x1, and here x1 need to write back before. So before this is not still ready, this is gonna get ready here, but we want it here in decode. So this is dependency. This is actually something that we need to fix. But this dependency cannot be solved using just one feedback from memory to memory. So memory to memory was like this. We can't solve it with that because the output is after reading from memory. So it's after. So this feedback can solve it. But that feedback is a little tricky because it's going backward. So you need to have that feedback, but still you cannot use this feedback. You need to have one stall and then use that. So in this case, you need to actually have one stall and then use that. So forwarding is not always enough. Data from a loaded word or loaded double word, whatever, is only ready after memory. So next instruction may need it earlier, so cannot forward data backward in time. So that's a interesting thing about load use. So cannot forward data backward in time. So what we need to do, the solution is to put bubble or a stall. So a stall means we are freeze everything. We are freezing everything and we are just changing one clock later. We're going to see how a stall works. We can implement the hardware as well. So, but in this case, as you can see, still we are getting from memory to execution. But this time is possible. We are not going backward. We are in the same time. Any question about that? So why then we can't solve load use with normal forwarding? Because we cannot go backward. So because the output of load is ready in memory after memory, but we want to access that in actually execution time. And execution is before memory. That's why we cannot go backward. To make it happen, still we need that actually forwarding pass. We need this forwarding pass, but we need to put a stall as well. So to solve the problem of load use, we need to use two things. First of all, one pass from memory to execution. Another one, put a bubble or put a stall. Two things we need to can solve this problem. Okay. How we can do forwarding in Verilog is because Verilog actually makes everything like life easier. Imagine you want to do all of this in hardware. It's so complex, but Verilog is kind of simulating everything very easy. We need to do two things in Verilog. First, we need to detect dependency. We need to, first of all, see dependency exists. So, and then when dependency exists, you can forward data from, based on type of dependencies. You want to get dependency from, for example, memory or from ILU or from memory. So you can get that. So let I explain a little bit here to see what's going on. So this is the main part. So first we have, this is for, let's just consider one of them because ILU has two parts. This is ILU. Write it somewhere else here. Okay. This is ILU, and ILU has two input. We call it A input and B input. But this can go from three paths. So we need to have a multiplexer to decide this goes from where. One is the normal that we call it, for example, let's do for B. Instruction decode, execute B, for example. This is the normal one. Here is A, here is B. Where else it can be? It can go from memory to memory to write back value, or it can go from execution to memory exmem execution memory ILU output. So these three ways, we need to choose which one is true. Is just a normal one, or there is dependency. If dependency exists, one of these two actually are active. Like, for example, this is a multiplexer. This is 0, 0, 0, 1, 1, 0, and 1, 1 is not happening. We just have 3 inputs, for example. Okay, so, and this is the ILU. ILU, arithmetic logic unit. So how we can check that, how we can do this, detect this dependency, we first of all, from here we see which one is correct. Are we working with source 1 or source 2? If we are with source 1, we are in this part. If we are source B, we are in a second part. We are in a B in. So I'm just going to explain one of them. That is this one. Is for source 1, and it's for actually forward from memory. Okay, if the forward from memory, what is this part? This is actually the important part. This part. This is saying register destination, and register destination from previous stage or a step is equal to source. This is source. Look at that, source 1. Register source next step. So register source in next stage is equal to previous destination. So this means hazard, isn't it? So from here we can detect that we have problem. So how we can solve it based on which one of these situation happening, we have 2 cases. We are considering A of, for ILU in, A in, coming from, if this condition happen, coming from memory out. If this condition happen, come from memory. So one of them coming from ILU out, the other one ILU out, and this is memory out. So as I explained, this is going to solve the situation that we had. Let's go back in here. So it's going to do these 2. It's coming from memory or coming from ILU. So you easily, with hardware description language in Verilog, you can implement these complex things, you know. Of course, you need to know some information, like, for example, these values are okay or wired, like from instruction fetch, instruction decode, register. You took some part of that, you know, you just got some wire out for register source and register destination. You can do that in Verilog. You can get wire from register. So the Verilog makes everything simple. But hardware is like that. Let me clean the hardware is like this. So you have one small control unit like brain that do this forwarding. So this forwarding brain make decision based on those you know, conditions that happening and dependencies specified. This multiplexer input actually route it from here or from here. As you can see, you can get from here one of the input, or you can get from here. So this is deciding, this forward unit decides, like a control unit that makes that happen. This control unit with very low happening here. You don't need to design the control. It's just this assignment that you are doing here is just control. And here is just like a switch for us that decide the in. This is like a multiplexer for us. If the input is this gonna go input. If this is happening, if this is true, this happening, as none of them happen, the input gonna be the normal ID execution A. Any question about this? You're gonna see something similar to that in that piece of code that you're gonna run. You don't need to do something extraordinary, something very complex. You just need to copy and make that happen. However, that's not easy too. Probably you need to fix so many things to that works. But still, and I want you also understand what's going on with the part in that code, the meaning, and which part is related to forwarding. I'm gonna ask you some questions, of course. But it's simple. I know you are so busy in these times. I don't want to make it loss of time. But at the same time, I want you to learn too. Okay, so this was how we can do forwarding or bypassing in Verilog. And this is the hardware. Let's do this example. Okay, let's do this example. I'm just gonna run the iClicker. Let's see everything where here. Start that. Then go pool. Start the pool. Okay. Good. Let's see. Let me explain it a little bit. I'm talking about considering two instructions here. RISC-V, load and store. I already talked about that, but I want you to understand what's going on. We are using same pipeline, 5-stage in this computer, and a standard forwarding is used. A standard forwarding means from execution to execution, there is feedback. From memory to execution also is feedback. But here, we want to see if these two can solve this problem. First of all, you need to see if any dependency exists. Is any dependency exist? This is read the memory and put it in X5. And here we are using X5 and write it back to memory. It's like two index of array that we are copying from one to the other. Is any dependency here? Yes or no? Yes. Yeah, because it's like an array. You're copy from one to the other one. Same part, 0, 0. So it's depend on each other, depend on X5. This X5 is equal. You're writing here, reading here. Reading and writing at the same time. Which one is the correct? Let's see what you mentioned. Okay, so the distribution is not normal. So it means, okay, it's getting normal. Okay, most of you guys thinking, let I explain. No hazard occur. So of course, hazard happen if we don't, we have execution feedback and memory execution feedback, but here we need memory to memory feedback. We need memory to memory feedback. So first of all, we have hazard. And is it the standard ILU forwarding? No, because it's from memory to memory. 3, a stall is required because load data is not, you can read the rest, not ready, I think ready in time. And why I can't move this? Oh, yeah, okay. The other one is the special forwarding path from memory from memory write back to data memory input is needed to avoid the stall. Okay. Now still most of you guys selected C, but this is not happening with one stall. We need more than one stall. But with forwarding, we can solve it, but not normal forwarding, not this forwarding, not this forwarding. We need, as I mentioned before, we need memory to memory forwarding. So memory is this, the output of this is the memory. I don't know why it's not writing this here. Anyway, here you have memory, and mem write back register. You need to get this and bring it inside as an input. You know, this is what I'm saying here. To get input, so this is what you need. This is a data memory as an input. So you need to have one feedback from outside the output of memory to input of memory. It's called memory, or we didn't call it here. We just said we need a feedback from memory to a memory write back. This is memory write back register to the data memory input, the data memory input. So this is the correct answer. This is the correct answer. Yes?
Porting from decode to memory, like memory to decode, which would require you to go back, because it's just
decode?
Yeah, because like from the decode stage, because the store word is getting
yes, we can, but we want to make it shorter. The reason of using feedback is to bring it anytime we want it. We are adding a hardware. We don't need to bring it to the decode. Yeah, in real situation, if I ask you how many stall happening in that without those forwarding, yes, you need to say, okay, we need to use it at decode. So how is possible to go decode? You need to go down in, multiple stall, like 2 stall at least you need to put to solve it. But when you are using feedback, you don't need to use it in decode anymore. You can bring feedback anytime you want it. When you want it, in a start of memory. Here you want it, because you want to write this to the memory. When you want it, here. You just need to put one multiplexer here to select which one go in. Did you get it? So the D is the correct answer. You didn't get it? No? Okay. Anybody understand what I said? What? Yeah. Do you want to explain? C. We need more than one stall. That's why one stall cannot solve it. We need more than one stall. Yes.
So but D implies avoiding a stall, right? A stall is needed regardless, right? Like,
no, we don't need a stall anymore. Why we need a stall? We are in the same time. We are not going back in time. We are still in memory. We get from output to input. Why we need a stall?
Well, exactly because of that one, because then you have to go back in time to forward that. And like when for the load, right? You're only going to be able to get the data from memory at the end in the memory stage. If your next instruction is directly under it in the pipeline, when you're reading from the register in the decode stage, you have to pull from memory, which is going to happen like 3 stages in the future, which you can't pull back from.
Let I draw it. I'm gonna draw it. Okay, your question?
I was just gonna I think I understand what you're saying. It's like because you're writing the X5 into like the next instruction, you don't it's just there for when the instruction goes through the entire phases of fetch, decode, whatever. So there's no memory error or whatever. Like the data is ran from that memory to the next stage's memory, so it's there for it to be used.
It can be used, yeah. I'm gonna draw them, but it's hard to draw. I gotta go back to show in this example that I had. or am I going forward or backward? Sorry. Yeah, here. Let I clean this. So what we have here, we have load and store. This is using x5, 0. I don't know what was that, but it was something like x1, 0, x1, x2, sorry, because we are copying from, okay, any something like that. But this x5 is a dependency part. So this, this is the dependency part. So let's see what's happening. What I'm saying we are getting from here to here, from this to this. Is it possible? This is just there. I'm saying we are not going back in time. We are get from here to here. So that's the time. Time 1, time 2, time 3, time 4. We are getting from here to here. This can use it without any problem. You don't need to go back. You don't need to go back from here to decode. Decode is here. Why we go here? We need it here. We need it before memory. You just can get one feedback to solve it. Anytime we go backward, that's not happening. That's not possible. But for example, here we did the same. We got from here to here. This is possible. This is exactly same as this. We can do that. So this is actually memory to memory feedback. However, in RISC-V, we don't have that. We just need we put it for compilers to solve it. Okay, so we explain this and this. Okay, so let's go. I think we are out of time, so let's finish this slide as well. This is how we can do scheduling. When we use load use, I said we can solve load use without the stall. In this sample, we have 2 load use, one here and one here. So the mechanism or the method or the algorithm that compiler used to fill this stall is to find after this gap, look for instructions that are independent instructions. Instructions are independent. I can write it up. Independent when they are independent, if does not use the result of the previous instructions. When it's not using the result of previous instructions, that instruction is independent. Is this independent? This is using x0 and x0 is not used. So yes, this is independent. But if the compiler is smart enough, we can have 2 stall here. What about this one? This is also independent because it's also using just x0 as an input, and x0 is not used here. X0 is always 0. So if we move this to this slot, to this part, to this gap, we're going to solve those both of these 2 problems at the same time. So the compiler needs to be smart in this case to find the proper. But there is multiple solution for that. We can move this one, or we can move this one. I'm saying move means put it in this gap, put it in this between load and add, because load and add makes a problem. Even though we have actually forwarding, still we need one stall. To make this stall, to fill this stall, we need to find independent instructions. The first independent is the add, SD. The other one is load. But if we choose load, we're gonna fix two problems at the same time. Why? Because between these two, we fill this gap, and between these two also we have two gaps now. So everything's solved. So the compiler needs to be smart enough in this case to find which one is better to actually do code scheduling. This is called code scheduling. Because we are changing the instruction places in the program without having problem. We need to see nothing gonna happen. If we move this from here, everything's okay. Any question about that? But there is, as I mentioned, there is multiple solution for that. You can use this and use this and put it in this. Move this and put it here. Oh, no, here is not, because X5. Oh, wait a second. This is dependent. I made mistake. There is just one solution. This is, yeah, we are using this X3 makes dependency. So here, this is a store. We are storing this. This is not, this is actually input. This is input, so this is dependency here. As you can see here is dependency. I didn't consider that. So it's just one solution actually. But let I highlight that. So you have dependency here. This is also dependency. And this is also dependency. Look at that. And this dependency is like ILU store. For a store, you need to consider that this is input and this part is output. You are storing this inside the memory. Any question? But with just moving this load up, you fix the problem of load store. Even though you have load, but this load doesn't have dependency. They don't depend on each other. Okay, I'm just gonna explain a little bit this and make it a day. So for hazard, so we need to understand that how we can make hazard in a pipeline. So hazard means what? Hazard means we need to keep instruction. We keep instruction, but we are just wasting one time. We have another control for detecting hazard. When the hazard detect with just checking to see dependency exists, we just need to make the control unit to create all zero. Then controller makes all zero. So I mean, write back becomes zero. Memory read, memory write becomes zero. The execution becomes zero. Still ILU working, makes something, but is not going anywhere. So the result's gonna be still we have the instruction here. We just make everything zero, and when and here too, look at that program counter. Program counter write is zero. It means it stay the same. Program counter is not changing because we put the controller of writing zero. So nobody can write on that. Also, we put the control signal of this instruction, fetch instruction, decode, also zero, means this is gonna stay the same as well because it has instruction on it. We don't want to flush it. This is different between stalling and flushing. We're gonna see flushing next class. Okay, so any question? Okay, have a good day then.
I think I did
swear the first one was